Hello students. One more example on similarity of matrices. Here I am going to discuss if the eigenvalues are repeated, then how to find the AM and GM. So example is given to you. In this example, let us start with the trace because it is required for eigenvalues to find eigenvalues. So trace is equal to -9 plus 3 plus 7. So this is equal to 10 minus 9 equal to 1. Let us calculate SMD, which is M11 plus M22 plus M33. If you simplify this, we will get -5, and determinant of A you can find using calc also, which is equal to 3. So after finding all these, we are going to write the characteristic equation lambda cube minus stress, which is 1 into lambda square plus SMD minus 5 into lambda minus determinant of A equal to 0. So we have the characteristic equation lambda cube minus lambda square minus 5 lambda minus 3 equal to 0. If you enter this equation in the calc, we will get roots 3 and -1. Here the third root or third eigenvalue is repeated, that we can find using the concept that sum of eigenvalues is equal to trace. So you can use this logic. We have two values 3 and -1, and suppose we need to calculate lambda 3, and that is equal to trace. So 3 minus 1, this is 2 plus lambda 3 equal to 1. So lambda 3 is equal to 1 minus 2. So lambda 3 is equal to -1. So here -1 is repeated 2 times. After finding eigenvalues, we will move to find eigenvectors. So for lambda equal to 3, no doubt definitely we will get one vector associated with this, because lambda equal to 3 is not repeated, and the vector associated with this you can try, we have done so many times. So vector is 1, 1 and 2. My main focus is again how to find eigenvector associated with lambda equal to -1. You can put value of lambda in the equation a minus lambda into x is equal to 0. If lambda is -1, so we can write a plus I into x is equal to 0. It means that you have to add 1 in the diagonal elements of A, matrix A. So -9 plus 1 is -8, 4, 4. -8, 4, 4 is second row. -16, 8 and 8 is the third row. Now we have done this type of example in previous videos. Here if eigenvalue is repeated, we have to reduce this coefficient matrix to row echelon form. So I'm going to reduce it to its row echelon form by using some row transformations. Here -8 and -8, these coefficients are same, so I'm going to use the row transformation R2 minus R1, and to get here 0 in place of -16, I'm going to use R3 minus 2 times R1. So after using these two operations, the given matrix becomes -8, 4, 4, and last two rows gives us 0, and here x1, x2, x3, and the right hand side is the 0 matrix. So this is reduced row echelon form. So this is reduced row echelon form. Now we can find the rank of the coefficient matrix. Rank is here 1. Number of non-zero rows in reduced row echelon form represent the rank. And number of variables here, which is x1, x2, x3, they are 3 in number. So number of linearly independent eigenvectors, we can denote it by S, which is n minus r, that is 3. R is the rank, which is 1. So 3 minus 1, this is equal to 2. So it implies that for lambda equal to minus 1, which is repeated 2 times, it has 2 eigenvectors associated with this. So I'm going to consider here for two variables, suppose x2, I'm going to take it as s, and x3 is equal to t. You can put these values in the equation minus 8x1 plus 4x2 plus 4x3 is equal to 0. If you divide by 4, this is minus 2x1 plus x2 is s plus x3 is t is equal to 0, or you can write x1 is equal to 1 by 2 s plus t. Now here s and t are arbitrary values we can put. So I'm going to put s as 0 and t as 2, and after that I'm going to interchange s as 2 and t as 0. So if you do like this, you will get two vectors associated with this. So first vector x2 with the first set. Okay, here if I put s is equal to, you can see here s is equal to 0 here if I put, and t is equal to 2, t is equal to 2, x1 is equal to 1. So x1 is equal to 1. X2 is itself s is there, which is 0, and x3 is itself t is there, which is 2. So second eigenvector is 1 0 2, and the third eigenvector along with the last set of values, again s is 2 and t is 1, so x1 is 1 in this case, then x2 which is s, which is 2, and x3 which is t is equal to 0. So 1 0 2 is your second eigenvector, and 1 2 0 is your third eigenvector for lambda equal to minus 1. Now we will discuss about AM, GM, and D and M. Okay. Now see here, AM I'm going to calculate. So just recall here, the values of lambda are 3 minus 1 and minus 1. Okay. So AM for lambda equal to 3, AM for lambda equal to 3, number of times this 3 is there in this eigenvalues, so which is only once, so AM is 3, and this has only one eigenvector associated with this lambda equal to 3, so GM is also 1. Now let us discuss. For lambda equal to minus 1, this is repeated 2 times. So you can say that AM for lambda equal to minus 1, this is repeated 2 times. So this is 2. And just now we have seen there are 2 eigenvectors associated with this lambda equal to minus 1. So GM is also 2. So AM is equal to GM for lambda equal to 3 as well as for lambda equal to minus 1. So we can say that the matrix is diagonalizable. You can see these are the few points. Here A is diagonalizable. and we can find D and M also. So it is D here. D is a matrix whose diagonal elements are eigen values of A. So this is D, and M is the model matrix whose columns are eigenvectors of A. So for lambda equal to 3, we know the eigenvector is 1, 1, 2, and for lambda equal to -1, we have eigenvectors 1, 0, 2 or 1, 2, 0. So in this way, we can find D and M if matrix is diagonalizable, and matrix is diagonalizable if and only if AM equal to GM. So these are the first point we have seen in the previous video. If all eigenvalues of A are distinct, okay, in that video we have seen 0, 3 and 15, these were the eigenvalues, then A can be diagonalizable or A is diagonalizable. Okay, now in this video we have seen this case. If eigenvalues of A is repeated, so here eigenvalues 3 minus 1 minus 1 repeated, then A may be diagonalizable or may not be diagonalizable, but here A is diagonalizable. Okay, now in the next video we will see that eigenvalues are repeated but A is non-diagonalizable because it totally depends upon AM and GM for each lambda. In the third point, if the algebraic multiplicity and geometric multiplicity of a repeated value are equal, then A is diagonalizable. If the algebraic multiplicity and geometric multiplicity of a repeated value are not equal, then A is non-diagonalizable. This concept we are going to use. So thank you. I hope this is a diagonalization, condition of diagonalization is clear to everyone. Thank you.